Welcome. In today's video, we're going to look at the expected return of a portfolio. In the previous video, we looked at the expected return of a single asset. So the idea today is to extend that concept to the idea of an entire portfolio, which is effectively a collection of assets. So let's suppose we're given a portfolio of N assets. And each of those assets, we're going to say, has return 1, return 2, all the way up to return N, which represents the return of the nth asset. And then suppose an investor allocates a certain percentage of their wealth to each asset. So what we're going to do is we're going to let WI denote the percentage of wealth allocated to that ith asset. So for example, if we had two stocks, stock 1 and stock 2, then what we could allocate our percentage of wealth, we could say, okay, 20% will be in stock 1, 80% will be in stock 2. Something like that. That's what our WIs represent. So we're going to denote the total return of the portfolio as R subscript P. So, in other words, we can actually say that the return of the portfolio, as you can see here, is given by the multiplication of the allocation to portfolio 1 times the return of portfolio 1 plus the allocation to stock 2 or to asset 2 times the return on asset 2, all the way up to the multiplication between the allocation to stock N times the return on stock N. So again, that will be the total return. So you can think of the total return sort of as a weighted average of the returns of each of the N portfolios, depending on how much you allocate. The more you allocate to a certain stock, the more that the return will look like that certain stock. So what we're going to do here is we're actually going to use some sigma or summation notation, and simply that summation notation is saying, well, if you go from I equals 1 to N, and you take WI RI, that is of course the equivalent of the expansion up the top here. So you cycle from I equals 1, you replace wherever you see I with a 1, so that would be W1 R1, which is that first term. Then you go to the next term in the sequence, which would be 2, hence why you get W2 R2 in the next part of the sequence. Now, what we're going to do actually is we're going to actually formalize this as W transpose times R, where W and R are actually vectors. So this is another simplified way we can write our notation, and that simply gives the top hand here. So note, if WI and these weights represent the proportion of wealth, remember the proportion of wealth invested into an asset I, it follows that the sum of the proportion of the wealth allocated to each asset must sum to 100. In fact, it's 100%, or in other words, 1. In other words, when we were discussing before how I was saying you can add or you can invest 80% in stock 1 and 20% in stock 2, it's important that you obviously couldn't invest 80% in stock 1 and 40% of your wealth in stock 2, because that would equate to something like 120% of your wealth. You can't invest more wealth than you already have. Although, and I must point this out, what we could have is, and I think I explain this on the next page in a little bit more detail, but suppose, for example, we did invest 80% in stock 1, 20% in stock 2, which would give us 120%. 80%, 40% in stock 2, so which would give us 120% overall. Then what we would need is we could invest and I'm only going on mathematics here, what if we invested negative 20% in a stock or in a portfolio? In other words, what does it mean to invest negative 20%? We would short the stock. In other words, we would borrow against the stock or the asset. But I'm going to go to the next slide. We're going to deal with additional constraints, and two such constraints might be described below. So the first constraint is that all the weights on the portfolio must be greater than 0. In other words, you can't invest something like negative 20%. So this constraint effectively prohibits an investor from investing in a negative amount of wealth into an asset. And another way you can think about that is borrowing against an asset. You take the asset now and you give it back in the future. Borrowing against an asset is also known as short selling, but since the 2008 global financial crisis, many regulators have banned the practice. Now, the other type of sort of constraint that we're not really going to focus on too much today, but it isn't a constraint nonetheless that is possible, is this idea that the portfolio weight or the percentage of your wealth allocated to any particular asset is restricted by a certain value. So this constraint, and here I've specified it as each weight or each asset weight must be, each asset has its own restriction weight. So I've called that W or MI. In other words, asset 1 might have a restriction of 20%, asset 2 might have a restriction of 30%, whatever, going on and so on and so forth. But the important point is it prohibits an investor from investing a significant proportion of their wealth into one asset. In other words, it sort of avoids this concentration, this risk of concentration where you have a portfolio, you invest heavily in this one asset in that portfolio. If that asset performs poorly, then your entire portfolio performs poorly because of how much or how concentrated your allocation is to that particular asset. So in this sense, and I suppose it makes sense in this way because ideally the idea of portfolio and optimization is we want to remove the sorts of individual risk, the idea that by constructing a portfolio, we can actually de-risk our portfolio or reduce the risk of our portfolio using diversification. So we'll leave that for there now, but it's something to think about in the back of your mind always. So now what we're going to do is we're going to construct a way to find the expected return of a portfolio. Remember, we already found a way to express, or we found a random variable back. If we go back here, we found a way to express the return of the portfolio as a random variable, as a sum of other random variables here. So now what we're going to do is using this, we're going to find a way to find the expected return of the portfolio based on this summation. So going here. So what we're going to do is we're going to let mu I denote the expected return of the ith return, or the ith asset, the expected return of the ith asset. So how do we find the expected return of the portfolio? Well, we can find the expected return of the portfolio by saying the expected return of RP is equal to the expected return of the sum of that sum. Remember, RP, the random variable, is the sum of the weighted allocation of all the individual assets. Now, what we're going to do in the next step is we're going to say, well, we know how expectation works. The expectation of a sum of random variables is the same as the sum of expectations. Hence why we can bring through that expectation sign into the summation, and we can actually bring it through here into the individual assets. or the individual return of the assets themselves. And of course, in the next step, you'll see that we've replaced the expected value of Ri with mu I. Again, we labeled mu I here as the expected return of the ith asset. And so again, using that notation that we had before, where we could write the summation simply in the form the weight vector transposed multiplied by the expected return vector mu. So we're going to have a look exactly in an example of how this works, hopefully on the next slide. And here I've just made a note here. We've made a use of the linearity of expectation, as I was discussing before, that the expected value of a sum of random variables is equal to the sum of the individual expected values. So let's now go here. So here's our question. Suppose an investor invests 20% of his wealth into asset 1, 30% of his wealth into asset 2, and the remainder of his wealth into asset 3. If asset 1, asset 2, and asset 3 have expected returns of 10%, 15%, and 20%, determine the expected value of the portfolio. So again, what I've said here is let the random variable Rp denote the return of the portfolio, Ri denote the return of asset I, and Wi denote the proportion of investors' wealth allocated to I equals 1, 2, 3. I'm just really formalizing what we wrote before. We've already really got it here, asset 1, asset 2, asset 3. I'm just formalizing how we're going to define these random variables. So, the expected return of the portfolio can be thought of as the weight 1 times the expected value of the return of asset 1, plus weight 2 times the expected return of asset 2, and plus weight 3 times the expected return of asset 3. And simply put, this gives you weight 1, which was, we were told in the question, is 20%. So I got 20% times the expected return of asset 1, we were told in the question was 10%. So I've got 10% here. And a similar process for asset 2 and asset 3. You've got your 30% invested in asset 2, 50% in asset 3, return 15%, return 20% respectively. Multiplying those out all together and giving you the sum, you've got 16.5%. And that's simply how we find the expected return of a portfolio.